Well, hello, VEST scholars. It's time for you to explore sea level change. Your Module 6 lab is looking primarily at that. It's important for you to understand that sea level change is quite complicated. Of course, we'll go back to you understand, of course, with global warming occurring as it is, NASA satellites and tidal gauge stations are generally recording a global or a eustatic sea level rise of on average, about 3.2 millimeters per year. And you can see from 93 for the satellite data, at least from 93 on out, it's been steadily going up. And from 1870 with tidal gauge data, we can work that in as well. So that's clearly both trends are very positive. You've got your minor fluctuations, but they're generally very positive. And you can go and download this data yourself and make your own curves. It's great. But really, what's going on here with sea level? Sea level is quite complicated. So let's talk about this a little bit. There are two main types of sea level change, eustatic and isostatic. Eustatic sea level change are global things. We'll look at a couple of global eustatic sea level change curves here in a moment. But generally, we're looking at the size of ocean basins changing, or the volume of volumetric measurements of the water in the oceans changing, and then tectonic events, breakup of supercontinents and the formation of supercontinents and mountain building or orogenic events, things like that. Isostatic sea level change is more localized. It could be continental-wide, or it's not global. It could be continent-wide. It could be just the east coast of the U.S., the southern coast of Alaska. These are isostatic changes that occur. And a lot of times they're from the melting of glaciers. Of course, melting of glaciers, does two things. You're adding water to the ocean basin, which does actually raise sea level. And you're also removing mass from the top of a continent, which causes it to rebound or raise up. You're taking weight off of something. You can imagine sitting in a pool on a floating mattress and having somebody jump in with you, or jump in on the mattress as well. The mattress will sink. That's kind of what happens with glaciers in a way. But these are things that are factors between these two types of sea level. Eustatic sea level is a little more complicated because there's a lot of factors involved, and a lot of them are pretty involve some pretty intense geoscience, but you could spend semesters studying this stuff in college. But tectonic changes, I would pause the slide and think about these for a little bit, do a little bit of research on your own if you're really interested in pursuing this further. But bottom line is, these eustatic changes are global averages that take a long time generally to occur in terms of tectonics, in terms of erosion of mountains, formation of mountains, things of that nature. These are on the orders of hundreds of millions of years in some cases. But if we look at an example of eustatic sea level fluctuations, we've got a couple of curves we're going to look at: the Hawk et Alia curve, as well as Halam et Alia and the Exxon sea level curve, all of which have their different interpretations. But they generally agree that, of course, here the Hawk curve is a little different, but generally the sea levels going down towards the end of the Cretaceous, from the formation of Pangea, breakup of Pangea, you get a drop in sea level, and then in the Tertiary things pick back up again a little bit. With these curves, think back to Pangea, which is at the end of the Permian, beginning of the Triassic. You had a supercontinent. Sea level was lower then, or about what it is today, actually. If you go back in time to where the continent was still broken up, sea level was much higher, up to 400 meters higher than it is today, potentially, with this curve. And then, of course, you go back further in time to the supercontinent Rodinia, which existed prior to the Cambrian explosion, about 650 to 1.2 billion years, 650 million to 1.2 billion years ago. Sea level, again, with the supercontinent was lower. So these are tectonic things. Obviously, sea level rise we're seeing today is not being affected by tectonics, but these are things to consider. So without belaboring this too much, you understand, of course, that the Earth's crust or lithosphere is broken up into tectonic plates. And this is a relatively simplistic version of that. There are smaller plates that exist around, but nevertheless, they're going in different directions. You have some areas where plates are coming together, and you have subduction zones like you do around these convergent boundaries around the Pacific Ocean. And then you have divergent boundaries. Both cases, and all these boundaries, new volcanics are occurring and new magma is erupting, that magma tends to be the same composition as, say, the magma erupting here at the ocean at the Mid-Atlantic Ridge is the same as the magma that makes up the ocean basin here, except that it's less dense when it's new than it is when it's old. The oldest Atlantic Ocean lithosphere is over here off the east coast of the U.S., and it's about 180 million years old. It's much more dense. It's the same chemistry, but much more dense than the Mid-Atlantic Ridge magmas over there by the Mid-Atlantic Ridge. So that, of course, is an isostatic reality. So that can affect sea level. So over time, the crust condenses, the lithosphere condenses, and it'll cause the continent to sink further down into the asthenosphere. So again, of course, just looking at the cross section of various types of boundaries, you have divergent boundaries where crust is being, or lithosphere is being produced, and then you have convergent boundaries where lithosphere is being recycled or subducted back into the Earth's interior. And of course, not to leave out the transform boundaries, but anyway, so these are situations that can cause sea levels to rise. You're going to cause mountain building events as you have convergent boundaries occurring, which lift up mountains, including all volcanic mountain ranges, which can cause sea level to appear to drop along coastlines like this. So that would be isostatic sea level regression, is what we'd call that. And then as these erode or weather and erode, you can actually cause a transgression, or what appears to be a transgression. So we call these cratonic sequences in the terms of really deep time. You don't need to worry about that term, but bottom line is, over long periods of time, mountain building events, continental collisions, continental breakups, they cause sea level change eustatically. And within those eustatic sea level changes, there are isostatic sea level changes occurring as well because of the cooling and condensing of rock and uplift of mountains in a particular area, causing the sea level to appear to move in different ways. So if we look at isostasy, isostasy is nothing more than just looking at the way that a block of something sits, of something of some density sits in the block of liquid, or in a body of liquid of another density, like an ice cube. So this block of lithosphere here, 2.2 grams per cubic centimeter, is sitting in a block of asthenosphere, about 3.3 grams per cubic centimeter in density, and it's only 10 kilometers thick. I can change the thickness. This is oceanic lithosphere thickness right now, and I've got the density a little low. I can make the density a little lower even, and you can see how it raises up. And as I cool and condense that volcanic material, that oceanic lithosphere, it'll sink further down into the mantle, or the upper mantle, the asthenosphere. If I make this continental lithosphere thickness, still it's the same density as oceanic right now, I would need to actually decrease the density for continental lithosphere, which is why continental lithosphere sits up above the ocean so much more, or, well, oceanic doesn't, because it's not only thicker, but it's much less dense than the oceanic. So this is another reason why continents, when you have more continental lithosphere, you actually change the sea level as well. But again, if I increase the density of it, it cools over time, or whatever, sea level can appear to go up or appear to go down, and that's an isostatic reality. That's what we call relative or isostatic sea level change. So this happens with glaciers, and as the climate warms, as the climate cools, glaciers can grow. And glaciers are massive, and they'll sit on top of the continental lithosphere, and they'll cause subsidence beneath them. And when you push down on the lithosphere, you uplift in other places, but sea level will be affected along the coastlines, wherever those coastlines are, as well as the mantle flow beneath. You can actually cause the mantle flow to change because of glaciers. Over time, of course, the glaciers melt, and as they melt, you're going to get uplift underneath where the glacier was. That's also referred to as isostatic rebound, and then subsidence in places that had uplifted before. And again, the mantle flow can be affected again. All of which to say that, as you take a glacier off, you're adding fresh water to the ocean, and you're also, which raises sea level in the shorter term, but over the longer term, the continent will lift itself up a bit out of the asthenosphere and cause sea level to appear to go down. That's isostatic sea level change. One of the effect of it going up with the added fresh water may or may not be greater than the effect of the sea level going down because of rebound. If you're not confused yet, and if you are, it's understandable. This is not straightforward. So when we talk about sea level rise, we're not just talking about a single variable here. We're talking about a lot of variables. So now let's see here. You are going to be looking at, when you look at sea level rise, again, this is the NASA data. This is NASA's worked through all these issues. This is the current sea level rise curve. But when you go to look at your, you'll notice that these tidal gauging stations aren't all uniform in their rates. So you have rates that are really intense from 9 to 12 millimeters per year and 3 to 4 feet per century. Then you have other rates that are actually going down, 12 to 15 millimeters per year or 4 to 5 feet per century. So here in the north, of course, the colder waters, the ocean water is not expanding quite as much as it is down in the mid latitudes, where you have the effects of global warming are more pronounced in the poles than they are around the equator as well. So again, you have changes going on in the middle of the ocean due to changes in weather and changes in expansion of seawater. But then you also have, you're melting. We've melted ice off of the continents for a long time, and all that ice was up here in the northern parts of Canada, and it came down, of course, into Ohio and places like that. But the continent is still rebounding from that ice not being there as much. There's still some, but as there used to be. And so some of this effect of sea level going down could be attributed to isostatic rebound of the continent and the apparent drop in sea level because the portion of the continent up there in Canada rises up, while in other places, the expansion of the water and the addition of the fresh water from the ice actually raises sea level along the coast in all these tidal gauging stations. And again, in the lab, you'll be looking at a variety of these, and when you click on these arrows, you get a nice description that pops up, and you can see a lot of really interesting data as you click through these things. Here's your tidal gauging station. So as you work through this lab, it's important to remember that though the global eustatic trend is for sea level for sea level going up at, as NASA has put on its website, 3.2 millimeters per year, and that trend's been going on since the Industrial Revolution, certainly. It's not straightforward and it's not uncomplicated. And that eustatic, or that average sea level, is one number to keep in mind, but there's a much more complicated and beautiful tapestry of things going on here. So spend some time on this and explore it. And if you have questions, ask your master teachers. Until next time, enjoy your work.